This is the third video in continuation of our presentation of our BTech project. In this video, we will be discussing the features to measure the document similarity. And the first these features are namely bird sentence encoder, cosine 1, cosine 2, cosine trigram, doxim NLTK, word to vec spacey embeddings, Jacquard trigram, longest common subsequence, n-gram containment, NLTK phrase toolkit, ribbon carp, sequence matcher, TensorFlow Universal Sentence Encoder. We're discussing all these features in more depth. This is just a short summary of the same. So if you'd like, then you can go through them. Below are the values mentioned as per the three examples that we showed you in the last video. These examples would give us an idea of how these features would work on different values or different types of uh, examples. The first feature is BERT sentence encoder. BERT stands for bidirectional encoder representational form from transformers. For sentence embeddings, we map a variable length input text to a fixed size dense vector. We feed this input into the BERT followed by a pooling layer to ensure that the vector is of equal dimensions. The embeddings for the BERT layer consist of three basic components: token, segment, and position embeddings. Uh, Here, it is to be noted that by pooling layer we mean that for two types of sentences, the vector form can be of equal sizes, thus we add the pooling layer. The output of the BERT layer are the word vectors, which are then passed from a softmax activated dense layer where the loss is computed, focusing mainly on the mass tokens to raise the context analysis. By mass tokens we mean the words on which we are emphasizing more. This model is much better than the LTSM, basically long-term short memory model, as it focuses on each word in parallel rather than just the forward and the backward direction of sentences, and is much faster as well due to working in parallel. The overall idea is that the words or phrases with similar meanings lie closer to each other in the vector space. The encoder block broadly consists of two parts: multi-head attention mechanism and a simple position-wise connected free-fall system. And the multi-head attention mechanism basically uh, uh, contributes to each word being given and worked on in parallel, and this ensures that inside for a particular word its relation with its sentence is associated to, and to get the meaning, to get the actual context of that sentence. And we use the position wise feed forward mechanism in order to transgress from one layer to other. Basically, we are using Google's BERT sentence encoder for encoding two documents into a vector and finding the cosine similarity between these two vectors. The next feature is cosine 1, conversion of input graphs into vectors, and then to make this vector we focus on the frequency of each word and we represent it in a vector format. Thus in this way the order of the words does not matter and just the frequency does. Thus we can calculate the inner product of these two vectors, and then finally we have the score. Now cosine 2. Cosine 2 also works with the same concept as of cosine 1. First, we tokenize the sentences into words and then we remove all the stop words such as the, a, and, etc. Uh, then these two vectors are formed of equal size to the union of the token words, and one vector represent for one of the vector it would represent one if the word is present or not. Basically, instead of focusing on the frequency, cosine 2 just focuses on whether a particular word is present or not in a script. And then we finally take the inner product of these two vectors and the score is generated. Cosine diagram. We make the following calculations such as term frequency, document frequency, inverse document frequency for both the documents. Document frequency for each word is calculated by counting the number of documents that had the given term, and term frequency is counted by how many times a particular term is present in one document. And here the word can be unigram, bigram, or trigram. We are using trigrams in order to account for context, the actual meaning uh, in a more suited manner. And then weighted vectors are computed using values of term frequency and inverse document frequency for both the documents. Then dot product is calculated between TF IDF vectors. Now Doxymantic, the next feature. Uh, this feature is provided by NLTK library, and the similarity formula returns a high value when the content of test document is either a subset or a superset of the registered document. It works on a set of words that are in common with the text and the registered document. The value of plagiarism is calculated using the concept of scam distance. It is a relative measure to detect overlap irrespective of the differences in the document size. Word-to-vec spacey embeddings. Um, this is really a standard approach that has been used from a long time, and word embeddings is a popular framework to represent to re- I'm sorry. Word embeddings is a popular framework to represent each word as a vector in a vector space of let's say 300 dimensions based on semantic context in which the word is found. Then we calculate the cosine similarity of these vectors, and this gives us an idea of how close the words actually are. The higher the cosine similarity, the higher the similarity of those words. But it is to be focused that we do not need word, we actually are working on sentences and paragraphs. So we rather calculate the mean vector of these words to compute for the similarity between sentences, and then we compare these vectors. During exhaustive testing, we notice that a cosine similarity of greater than 0.85 to 0.9 is rather a reliable indication that the sentences are very much alike. Checkout diagram. The calculation is same as the cosine diagram. We first calculate the term frequency, document frequency, and inverse document frequency for all the documents, and the weighted vectors are computed using values of term frequency, inverse document frequency for both the vectors. The Jaccard diagram is calculated between two weighted TF IDF vectors. Jaccard score is calculated by taking the intersection of two vectors and dividing it by the union of those two vectors. The next utility is longest common subsequence. It refers to the longest string of words that are the same between two documents. We normalize this value by dividing the value by total number of words in the answer, that is to be checked document. Use dynamic approach problem to find the value of LCS for those two documents. This feature is very handy to account for actual cases of plagiarism. The next feature is n-gram containment. N-gram containment is a sequential word grouping. Containment is defined as the intersection of n-gram words of a source text with the n-gram count of the student answer divided by the n-gram word count of the student answer text. Here, different values of n help us in analyzing the context of the inputs with respect to each other. We have experimented with different data sets, and we got to know that over different values of n, uh, let's say for higher values of n, if the scale if we the output that we get from this scale is on the higher side, then there are directly cases of plagiarism, as for more cases more the value of n, that means that same chunks are mostly used among those two documents. Next utility is NLTK phase toolkit. This features a combination of two factors, semantic similarity and word order similarity. Semantic similarity factors is computed by calculating the cosine similarity between semantic vectors. The semantic vectors are formed by associating the value of each word in a vector that is of the equal size to the union of those present in both the given inputs. In case the word from the joint set is not present in the input, then the word from the input which has the highest semantic similarity is associated as the weight of that vector. And for the word order similarity part, the weight of the words for one vector is featured by its position, and in case the word is not present, then the most similar word is given importance. Both these factors are then given weightage on a linear scale to compute for the overall score. We experimented on what this weight should be, and we are using different weights for different use cases. The next tool is ribbon carve. First, we filter the documents by tokenizing and removing the stop words. Then we calculate the hash values of each document and add it to the document type hash table. Hash value is calculated using the concept of a rolling hash. In rolling hash, we set the value of rolling window for which the hash values are calculated and keep adding it to the hash table. We set the value of the rolling window to be 3, and then we calculate the plagiarism rate using values of hash from both the documents. The next utility is Sequence Matcher. Sequence Matcher is a tool available in Python library deflib. It is used to compute the longest matching character string and then give the computed score of a normalization. For the following input, we get the mystery as output between my stock overflows and mystery. Continuing, this is the last feature that we have used, Universal Sentence Encoder. The universal sentence encoder encodes text into high-dimensional vectors and can be used for text classification, semantic similarity, clustering, and other natural processing tasks as well. The model is trained and optimized for greater than word length text such as sentences, phrases, or short paragraphs. It is trained on a variety of data sources and a variety of tasks with the aim of dynamically uh, accommodating a wide variety of natural language understanding tasks. The input is a variable length English text and the output is a 500 dimensional vector. We are using the model trained with a deep averaging network (DAN) encoder. Model is trained on Stanford National Language Interface SNLI corpus. The SNLI corpus is a collection of 570,000 human written English sentence pairs and also labeled manually. The sentence encoder differs from the word level embeddings as it focuses on the meaning of the word sequences rather than just individual words. Thus, we are using this encoder for semantic analysis. We would continue for describing the 4 utilities that we have built from the next video. Thank you for your time.